I'm back. It's time to talk about more trends in the periodic table. So, last time we learned about atomic radius and ionization energy. This time we're going to talk about reactivity and electronegativity. This information is to go along with the lab that you guys should have performed last Wednesday, or Wednesday in 2015, spring 2015. Alright, which is the periodic trends lab, where we looked at how calcium, magnesium, zinc, was it zinc, tin, all reacted in water and hydrochloric acid. And saw the different variations of reactions. All right. So this also goes along with the notes for lecture 3, short little guy on our trends for reactivity, electronegativity, and what kind of accounts for them. All right. So today we learned the fancy word inert. Alright, so back to our stuff. So we're focusing on reactivity and electronegativity. This is on your in your textbook on page 177. Actually, it doesn't contain anything about reactivity, but I think it's an important topic to talk about, and there's a cool trend on the periodic table that follows along with it. So last time we talked about atomic radius and ionization energy. Remember, atomic radius, half the distance between two bonded elements, so the same element bonded together, half the distance gives you your atomic radius in either angstroms or picometers. How big or small an atom was. And then we had our ionization energy. How much energy do you need to remove an electron? And we have our trend summarized over here. Atomic radius increases going down because of because of energy levels and electron shielding, and it decreases going across because of a stronger nuclear charge, which means it increases going the other way because of the opposite of a weaker nuclear charge. Same energy level. Right. And then ionization energy was the exact opposite. As you go across the period, it's increasing, so your atoms are getting smaller, it's hard to remove electrons from it. As you go up a column, a group or family, then it's also increasing. Your elements are still getting smaller, so it's harder to remove that electron because those protons have a really strong pull on them. Remember, noble gases are very stable, so they're not going to want to lose electrons at all. They'll have very high ionization energies. They'll fight for their electrons. So, first new trend we're going to talk about is reactivity. And reactivity is basically defined as how likely something is to react with something else, right? So how reactive is something. And we see there's actually two trends, and a little weird spot too over here. So for metals, there's this one trend. As you get closer to francium, as your element gets bigger, as your atomic radius increases, your reactivity also increases. So that kind of corresponds to the bigger the atom, the bigger the metal, the more reactive that metal is. So francium is extremely reactive. The nonmetals, being the exact opposite of metals always, has the exact opposite trend actually. So the more reactive one is fluorine. The most reactive is fluorine in that top right corner. Now if you're looking at this table, you'll notice something weird. There's a whited out group here. A group that is whited out for a good reason. So here are noble gases, our helium, neon, argon, krypton, xenon, radon, and undiscovered 118. And they're whited out because they're not reactive at all. They are known as what is called inert. They are very stable, so they don't really react with anything else. That's going to be because of their electron configurations. We can check that out on our ptable.com actually. Let's do that. So if you were to go to ptable.com, you can kind of see why these guys aren't very reactive. To do that, I'm going to switch tabs to orbitals. Remember S, P, D, and F orbitals? So the reason that the noble gases, these guys over here, are so unreactive, take a look at the center over here, so take a look at the orbital filling diagrams. The reason they're so unreactive is because all of our noble gases have full s and p orbitals. All the top level orbitals, all the highest energy levels, the outside of the atoms, are completely full with electrons, right? So if you look at the group next to it, they're all one away. You can see how each of them have 5 electrons. So if you're looking at bromine and the 4p orbital, it is 5 electrons out of the 6. It wants to be like krypton and have 6 in there. So these guys, our noble gases, are extremely unreactive because they're filled up. Their s and p orbitals are filled up. They're very stable in that sense. Switching back here. Alright, so that's our reactivity slide, how reactive something is. Has 2 trends, kind of weird, going towards either corner and ignoring the noble gases. It's a fun thing I like to add in. The next term is going to be electronegativity. And it's also known as electron affinity, so you'll see sometimes it described as electron affinity. And that's basically exactly what it is. Affinity is basically wanting something, right? So electronegativity is how bad does an element want electrons? How strong is going to pull electrons towards it? Specifically, electronegativity describes electrons in a bond. Something that has a high electronegativity is going to pull electrons towards it when it's forming a bond. So they're going to be closer to it than the other one. So here we can check out our favorite molecule, water. Right, 75% of the world is covered in water. And we have H2O. And if we look at it, these black dots in between the 2 atoms represent electrons. And this is a covalent bond, which we'll later learn is the atoms are supposed to be sharing the electrons. But if we look at it, this isn't a fair share. Oxygen's got them pulled right next close to it, and hydrogen is a far reach away from, right? So this is an example of how electronegativity comes into play and why it eventually becomes important. Water gets all its cool properties from its electronegativity. This partial negative charge and these partial positive charges give some really cool properties, including like the surface tension. But here you can see oxygen is definitely more electronegative than hydrogen because oxygen is pulling those electrons closer to it, so it has a strong affinity for electrons. Alright, now let's look at the trend for electronegativity. This one is a much simpler one than reactivity. So here, some things you notice that are similar to reactivity. The noble gases are like straight zeros on the electronegativity scale, our 1 to 4 scale. That's because they don't want electrons at all. Kind of think of maybe why they don't want electrons. It's mainly because of their perfect orbital filling diagrams, their perfect electron configurations. They're filled up in their outer s and p orbitals. They don't want any more. But all the rest of the guys aren't quite full in their outer levels. Electronegativity, who wants the most electrons? Let's try to figure that out. So it looks like the darker blue is the one that has the highest. So if we see our dark blue, kind of looks like hydrogen's pretty high, but that's a light blue. We see that fluorine is probably our top electronegativity guy, and from other tables you can tell that that's definitely correct. Fluorine is extremely electronegative, followed by oxygen and chlorine. So oxygen was beating up that hydrogen for the electrons. But in general, if we look at our trends, as you go down, looks like your electronegativity is decreasing. So as you go up, it's increasing. As you go across, looks like it kind of varies, but in general, it looks like it's increasing also. And that's the trends we're going to look for. So when we describe electronegativity, also known as electron affinity, looks like as you go across, it gets greater, and as you go up, it gets bigger. Just that one weird thing that noble gases don't count for electron affinity. They don't really want any more electrons. Alright, we could stop there and be satisfied, but I want to show you one more thing with these guys. So we talked earlier that the noble gases are happy are stable because their s and their p orbital, so the 2s and the 2p orbital for neon, is completely full. One reason why fluorine has such a high electronegativity and the electronegativity increases going from left to right is because of these electron orbital filling diagrams. If you see, fluorine just needs one more electron, one more down arrow to make it stable. It wants to be just like neon, right? So it really just needs just that little bit of electron and then it can be stable. And that's going to be the main reason that it has such a high electron affinity. Over here on our opposite end of the spectrum, so we saw over here, francium, other than noble gases, looked like it was the smallest electron affinity, electronegativity. The reason that's going to be is because fluorine doesn't, or francium doesn't want any more electrons, right? It would rather lose an electron. Because if we look at its orbital filling diagram, so I'll click on francium. If we look at its orbital filling diagram, its last S and P orbital that's full, or the 6s, right? It only has one more electron in there after the 6s and the 6p were filled. That's this one up arrow, and that's messing it up from being stable, right? So it really doesn't want any more electrons. It actually wants to get rid of this electron. That's why it has such a low ionization energy. It wants to get rid of this electron. It's fine to give it away. It still takes energy to take it off, but not as much as these guys going up higher or these guys going to the right. So it really doesn't want that electron because it could be so much more stable if it just lost it. Alright, so that's our general trends for electronegativity and reactivity. I just love the reactivity one. That weird split. Non-metals and metals fighting again. Alright, that's all guys. Have a good night.